This is Anthony Priscilla doing more trigonometry sum and difference problems with my trig class. This first one we're going to do simple. Oh, well, the instructions say graph the given expression. Don't do that. What I want you to do is use an identity, okay? Do it the way it did number one. I don't know why that person wrote that one, graph it and stuff. We'll discuss graphing more later on, okay? In fact, that'll be our big unit after this. We're doing this specifically without graphing it. So do this problem the same way we did the other one involving cosine. We did a couple of cosine problems like this. So sine 3 pi over 2 minus x. On this whole page, we're going to be using those sum and difference problems or identities for cosine. Let me write them out. All is one step. Not for cosine, it's sine. Sine, let's write this as just one identity. Sine A plus or minus B. It's sine cosine. Then the same symbol, so the top plus stays, or stays a top plus. The top minus stays as a minus. Sine, sine, cosine, cosine, sine. Same symbol in the middle. So that's what we're going to use to simplify sine 3 pi over 2 minus 1. Well, sine, cosine. Notice how I'm going. First angle, second angle. Same symbol, so this is going to be a minus. Cosine, sine. Sine, cosine, cosine, sine. Same symbol in the middle. Oh gosh, 3 pi over 2. Let's think in terms of a, on the unit circle, 3 pi over 2 would be right here. And what would that ordered pair be? How about a 0, negative 1? I nearly wrote negative 1, 0. That's why a 0 looks like a theta. It sure is 0, negative 1. So sine 3 pi over 2 would be negative 1. Cosine 3 pi over 2 is 0. So we have negative 1 times cosine x. That would just be negative cosine x. This minus is this one right there. 0 times sine x is 0. So is this just going to be a negative cosine x? Now follow what I did there. Sine 3 pi over 2 is negative 1. Cosine 3 pi over 2 is 0. So negative 1 times cosine x is negative cosine x. 0 times sine x is 0. Okay. So this would be what, a b? Oh, actually, okay, number 13. Okay, good. Let's do number 13 now. This is going to be one sort of like that problem 6 that we did just a moment ago. Oh, wow, this finished product looks sort of intimidating, doesn't it? It's not that bad. When it gets that bad, I'll tell y'all. So, I'm going to do number 13. Using those sine, cosine, cosine, sine identity. So I'm going to move this on up and we'll do number 13. And after class I'll post these videos here along with the homework. So if you came in late or if you're absent, in which case I'm speaking to no one. If you're absent, you don't hear me saying this. It'll be on there so you can look at it, okay? So let's see. This is problem number 13. says find the exact value of sine alpha minus beta, given that sine alpha is 12 over 13 and sine beta is 5 over 13. And unlike the one we did earlier where it told us which quadrants we're in, here it just says alpha and beta are between 0 and pi over 2. Between 0 and pi over 2, which quadrant would that be? Yeah, quadrant 1. Between 0 and 90 degrees. So that means x and y in both of these are what? Positive or negative? Positive. X is positive. Y is positive. R is always positive. I'm going to go ahead and put a little plus right here. Just so to show, sometimes students say, well, wait, what did you do with that part there about the 0 and pi over 2? That's what makes me know that x and y are both positive. Same thing over here. X and y will both be positive. These are problems very, we're going to have some problems. Well, I'll discuss that later. Okay, in terms of x, y, and r, sine is y over r, so 12 over 13. X squared plus y squared is r squared. Y squared, 12 times 12, 144. And r squared, what would that be? 13 times 13, 169. So subtract the 144. So we have x squared equals 25. X is going to be positive 5. Okay. Now we'll do the same thing with the beta angle. Oh wow, could y'all figure out just looking at this and what we did here, what's x going to be?
12.
Yeah, okay, yep, 12. I'll go ahead and show it anyway. X squared plus y squared is r squared. X squared plus y squared, 5 squared is 25. R squared, 13 times 13, 169. Subtract the 25, and y'all are sure right. We have x squared equals 144, so x has to be 12. Remember our teacher, Ms. McGowan, in the 8th grade, making us memorize things like 5, 12, 13. Because in terms of a Pythagorean theorem, a squared plus b squared is c squared. So if we had either two of these numbers, then we'd be able to figure out the third one without going through the work. But that was way before handheld calculators were so prominent. Now, what the heck are we asked to find here? Well, we're trying to find sine alpha minus beta. So that's sine, what's that little pattern? Sine, cosine, same or change? What am I going to do? Same. Sine, cosine, cosine, sine. Janet Clark was the one. Years ago, well, there were two high school teachers that I remember going through this. That was Janet Clark. Sine, cosine, cosine, sine, same symbol in the middle, and so forth. Cosine, cosine, sine, sine, change the symbol in the middle. Now, the alpha stuff I've done in blue. So sine alpha we were given, that was 12 over 13. What about cosine alpha? 5 over 13. Now, cosine beta, we weren't given that, but we have it. 12 over 13. And sine beta is 5 over 13. So the nice thing about doing, if you click view an example when you're doing this, I think they're going to go through using the Pythagorean identities and find cosine alpha and cosine beta that way. But the problem with that is, well, what if they didn't ask for sine? What if they asked for tangent? Then you'd have to go sine over cosine. Here, if you need to know tangent alpha, it's real easy, isn't it? It's y over x. Okay, or if for some reason you needed to know cotangent beta, you wouldn't need to with these identities, but if you did, it's x over y. So what would we have? 144 over 169, minus, let's see, 25 over 169? What's that going to be? I know the bottom number is 169. 144 minus 24 is 120. 119? 119 over 169. Any questions there?